Welcome to the Deep Dive, the show where we take a stack of sources, extract the most important nuggets, and give you the shortcut to being truly well informed. Today, we're plunging into a concept so fundamental, maybe so unassuming, that you might not even realize how much it underpins our entire digital world. Think about the word log. Maybe it's a ship's logbook, meticulously recording every event of a voyage, or a personal diary chronicling your daily thoughts. For software developers, it might bring to mind those plain text files filled with system messages, stuff that helps debug an application. These are all familiar, right? But what if I told you the simple, common concept is actually a deeply powerful abstraction? A foundational building block that underpins everything from cutting-edge NoSQL databases to, well, the very mechanisms of cryptocurrencies. It's far more profound than just text files meant for human eyes. Our mission in this deep dive is to truly unpack this humble log as a fundamental data structure, especially, in the context of distributed systems. We'll be extracting the most important insights from Jay Krepp's insightful book, I Heart Logs, helping you understand not just what this concept is, but why it's so utterly essential, and what it means for how modern data systems are built. We're going to uncover some surprising facts and connect all the dots for you, really give you a fresh perspective on how your digital world truly works. So when most of us hear log, we probably first picture something like maybe an Apache web server log file,
Yeah, exactly.
a long sequence of loosely structured messages, primarily there for humans to read. It's a record of events, sure, but largely for troubleshooting.
That's absolutely the common perception. But it's really just a simplified, almost a degenerate form of the deeper log concept we're exploring today. In the world of databases and distributed systems, a log is precisely defined as an append-only sequence of records ordered by time.
Append only, ordered by time. Okay.
And the crucial distinction here, and this is key, is that these logs are designed for programmatic access, not just human readability. Each entry appended to this log gets assigned a unique sequential log entry number.
Right.
Think of this number as its unique key, but also critically as a notion of time that's entirely decoupled from any specific physical clock.
Ah, okay, so it's its own internal time.
Exactly. This might seem a bit abstract at first, but it turns out to be foundational for reliable distributed systems. You can really picture a log as a fundamental data structure, much like a file or a table, but where records are strictly sorted by their order of arrival, by that log entry number. What's truly fascinating here is that this deceptively simple idea, this append-only ordered sequence, is at the very heart of recording what happened and when. For distributed data systems, where information is spread across many machines, understanding and agreeing upon this precise sequence of events is, in many ways, the core problem they're trying to solve.
It's the source of truth.
It's the ultimate source of truth, indeed. The log concept likely originated in the early days of databases, with roots tracing back as far as IBM's System R. Its initial purpose was remarkably similar to its modern use, to keep a variety of complex data structures and indexes within a database in perfect sync. And, critically, to ensure A to B properties, that's atomicity, consistency, isolation, durability, even if the system crashed.
Right, the classic database guarantees.
Exactly. Imagine a database suddenly losing power. The log becomes the authoritative source. It stores a complete ordered record of all modifications before they're actually applied to the main data. This allows the database to restore all its other persistent structures to a valid state when it restarts. It knows exactly what happened up to the point of the crash.
Okay, so it's about recovery and consistency within one database first.
Precisely. But over time, this foundational use evolved. It became a primary method for replicating data between databases. If you've ever heard of or worked with, say, Oracle, MySQL, PostgreSQL, or even MongoDB, you might know they use log shipping protocols.
Log shipping, right, I've heard that term.
These basically transmit portions of a log from a primary database to replica databases, ensuring they stay perfectly in sync. So in essence, the log in database internal serves two powerful purposes. It acts as a publish-subscribe mechanism to reliably transmit data to other replicas. And it's a consistency mechanism to precisely order the updates applied across those multiple replicas, making sure everyone agrees on the history. And this brings us neatly to distributed systems in general, because they face the exact same fundamental challenges as a single database, just, on a grander scale.
How do you distribute data across many machines, and how do you ensure they all agree on the correct order of updates?
That's the crux of it.
Right. And this leads us directly to what Jay Kreps, the author, calls the state machine replication principle. It sounds incredibly complex,
It does sound a bit intimidating.
but it's actually a surprisingly simple and elegant observation. The principle states, if two identical deterministic processes begin in the same state and get the same inputs in the same order, they will produce the same output and end in the same state.
Mhm.
Okay, that's a mouthful. Let's unpack it a bit. When the author talks about deterministic, what exactly does that imply? Can you give us maybe a concrete example of something non-deterministic that would break this?
Absolutely. Deterministic basically means the process will always produce the exact same output to the exact same input every single time. No outside influence, no reliance on timing. So think about multi-threaded programs where the output could depend on the unpredictable order threads happen to execute in. That's non-deterministic.
Okay, race conditions and things like that.
Exactly. Or programs making decisions based on something like get time of day, which varies constantly. A non-deterministic process is just unreliable in a distributed setting because replicas could easily drift apart, ending up in different states even with the same logical inputs.
Got it. And the same input in the same order part.
That is precisely where a log becomes indispensable. The log provides that precise, unalterable ordered input stream. It guarantees that all replicas receive operations in the identical sequence, ensuring they stay in sync and behave consistently. The log enforces that order.
Okay, let's make this really concrete. The book uses an example of a replicated arithmetic service, right?
Yeah, it's a good simple one.
Multiple machines, variables x and y starting at 0. If you send two operations, say x plus 5 and y 2, the final state depends entirely on the order. If you do x plus 5, then y 2, that's one result. But if you flip it, y 2, then x plus 5, you get a totally different result for y.
Absolutely. Order matters completely.
So the log, with its discrete sequential log entry numbers, acts as that universally comparable clock. It guarantees those operations are applied in the exact same consistent order everywhere.
It's the key. It eliminates that ambiguity, which would otherwise lead to inconsistent replicas.
It really is the key to maintaining sanity, and consistency in a distributed world.
That example perfectly highlights what J. Krebs describes as the fascinating duality between a log of changes and a table or a current state. Think about a traditional bank. All the individual credits and debits that flow through, every single transaction processed, that's the log.
The history of everything.
Exactly. The current account balances that customers see on their banking app, that's the table or the current snapshot derived from that history. The profound insight here is that if you have a complete, ordered log of every change, you can always apply those changes in sequence to perfectly recreate the current state of the table, or even any past state down to the transaction.
So the log is more fundamental.
It is. The log, in this sense, isn't just a record. It's the ultimate source of truth. It fundamentally flips how we often think about data. Usually we think of history being derived from snapshots, but here the current state is derived from the history recorded in the log.
That's a powerful way to put it.
It's very much like how source code version control systems work, actually.
Oh yeah, how so?
Well, a sequence of changes or patches you commit is effectively a log.
Right.
Each commit builds on the last in a specific order.
Right, your Git history.
Exactly. And your checked out code on your local machine is the current table or snapshot. When you get pull or update, you're essentially pulling down new patches from the log and applying them to your local snapshot to bring it up to date. And there are actually databases, like Datomic, which are built entirely on these log-centric ideas. For them, the log is the database. The tables are just views on the log.
Wow, okay. So we've talked about the log's power within individual databases and these sort of foundational distributed systems principles. But what does this all mean for you, the listener, and your organization's data? How does it impact real-world challenges like data integration, which seems to plague, well, pretty much every modern company?
Yeah, data integration is a huge one.
At its core, it's about making all the data an organization has available to all the services and systems that need it. Simple goal, incredibly hard execution.
Right, and it's a much broader and more ambitious concept than traditional ETL extract, transform, load pipelines.
Which usually just focused on populating maybe a relational data warehouse for specific reports, right?
Exactly, often a very limited scope. The author points out something he calls Maslow's hierarchy of needs for data. It's a great analogy. At the very base of this pyramid is capturing all relevant data and reliably getting it into an accessible processing environment. Reliable data flow.
And the problem is?
The problem is many organizations, maybe yours included, are desperate to jump directly to the fancy stuff at the top. Advanced analytics, machine learning, deep learning.
Right, the sexy stuff.
But they have enormous holes in the base of this pyramid. They lack reliable, complete data flow from their source systems. And the book argues this is completely backwards. Without that reliable and complete data flow, even a powerful Hadoop cluster is little more than, as he puts it, a very expensive and difficult to assemble space heater.
That's a good line.
The real insight here is that reliable data flow is the absolute prerequisite. It's foundational for any meaningful data analysis or system integration.
Okay, and two modern complications have made this even tougher, the book says.
That's right. First, data itself is just far more diverse now. 15 or 20 years ago, a typical company might only talk about transactional data.
Yeah.
Things like users, orders, product inventories, usually kept neatly in relational databases.
Structured stuff.
Yeah, but today we have massive amounts of event data. Think user activity logging every click, every scroll, every page view on a website, machine-level events from IoT devices, detailed system stats from servers.
The fire hose.
It's a fire hose. This type of event data is what companies like Google built their fortunes on, clicks and impressions. And it extends everywhere now, from your smart home to industrial factories. And this event data can easily be orders of magnitude larger than traditional transactional data, just sheer volume.
Okay, data diversity and volume. What's the second complication?
The second is the explosion of specialized data systems. We don't just have relational databases anymore. We now have distinct systems for everything.
Yeah.
OLIP databases for complex analytical queries, search engines, simple online key value stores, batch processing frameworks like Hadoop, graph databases. The list goes on.
Teradata, Espresso, Cassandra, SOLR.
All of those names. Combining this increased diversity of data with this explosion of specialized systems creates a monumental data integration headache.
It's like trying to connect plumbing systems built with completely different kinds of pipes and fittings.
That's a great analogy. It becomes incredibly complex and brittle. And that's precisely where the log-structured data flow comes in, offering a remarkably simple and, frankly, elegant solution.
Okay, what's the recipe?
The recipe is straightforward. Put all of the organization's relevant data into a central log for real-time subscription. Each logical data source, whether it's an application logging user clicks or a database table logging modifications via something like change data capture, effectively becomes its own log, or maybe a specific partition within a larger log system like Kafka.
Okay, so everything feeds into this central log.
Right. Then subscribing systems like a cache, a Hadoop cluster, a search index, a real-time analytics dashboard, they simply read from this central log independently. They apply each new record to their own internal store, and importantly, they keep track of and advance their position in the log as they consume data.
So they know how far they've read.
Exactly. And here's where it gets really interesting. The log provides a precise, logical clock for every single change across the organization. This means all subscriber systems can be measured against that exact point in time in the log. Makes reasoning about the state of different systems incredibly simple. You know exactly how current each system's data is relative to the log.
That seems powerful for consistency.
It is. Beyond that, the log also acts as an enormous durable buffer. This makes data production entirely asynchronous from data consumption.
Why is that so vital?
Because subscribing systems can crash, they can go down for maintenance, they can simply get overloaded and fall behind. With the log as a buffer, when they come back online, they just pick up exactly where they left off in the log. They consume data at their own pace without affecting anything upstream, without losing data. It builds resilience.
And the destination system doesn't need to know about the source.
Critically, no. The destination system knows only about the log. It's completely decoupled from the data's original source. It doesn't care if the data came from an old mainframe, a relational database, or a brand new microservice.
That decoupling sounds like a huge win for flexibility.
It's absolutely critical for building flexible, resilient, evolvable data architectures. You can swap out producers or consumers without breaking everything. And just to clarify, when we talk about log here, we mean it in a much stronger sense than just a generic messaging system or maybe pub/sub.
Okay, what's the difference?
The log, especially in systems like Kafka, implies much stronger semantics. Guarantees like durability, meaning your data won't be lost even if servers fail. Strong ordering within a partition, ensuring messages arrive in the exact sequence they were sent. An atomic broadcast, meaning a message is reliably delivered to all relevant subscribers or none.
Got it. These are necessary guarantees for serious data integration.
Exactly. They're crucial for robust data replication and integration at scale.
Now, Jay Krebs, the author of I Heart Logs, he saw this data integration nightmare unfold firsthand, right? at LinkedIn.
Yeah, he lived it. As LinkedIn grew rapidly, they were moving from a relatively centralized relational database model to this sprawling collection of specialized distributed systems. Their search engine, their social graph database, people you may know, various key value stores. Lots of different systems.
And connecting them was the problem.
Exactly. Each new system, or each existing system needing new data, required custom data pipelines to get data in and out. The book has this diagram, figure 2 to 5, showing the ON2 pipelines model, where basically every system had to potentially connect directly to every other system. It was chaos.
Sounds like a nightmare to manage.
It was clearly infeasible long term. It led to a huge number of errors and failures and became an immense operational burden. Just keeping the lights on was hard.
But amidst that chaos, there was an aha moment.
Yes. Krebs realized that even those messy custom pipelines were incredibly valuable, simply for making data available. The problem wasn't the idea of data flow, it was the reliability, the scalability, the manageability. They desperately needed automated, reliable data loads, and they realized they had very low data coverage across the organization because building all these fragile, custom links was just too difficult and error-prone.
So what did that lead to?
It led him and his team to focus on building Kafka, a system designed specifically to combine the best aspects of high-throughput messaging systems with this powerful, durable log concept. Kafka was designed to act as that central high-throughput pipeline for all activity data, all database changes across the entire company. One reliable place to get data.
And the fact that others followed suit is telling.
Absolutely. The fact that Amazon Kinesis, Google Cloud PubSub, and Microsoft Azure Event Hubs have since offered remarkably similar log-based services is a strong sign, as Krebs notes, that they stumbled onto a genuinely good, fundamental infrastructure abstraction.
Okay, so Kafka is the central log. How does this rethink something like traditional ETL and data warehousing?
It has profound implications. The older data warehouse model, often relying on periodic batch extractions for analysis, is great for certain types of reporting, sure, but it tightly couples the clean, integrated data to that specific batch query system, like Hive or Teradata.
Meaning the data isn't easily available elsewhere in real time.
Exactly. That valuable, integrated data is often locked away, unavailable for real-time needs, like instantly updating a search index, feeding a recommendation engine, or driving critical monitoring dashboards.
So what's the log-centric alternative?
A far better approach in this log-centric world is to have that central log containing the canonical data streams accessible via a well-defined API. Now, the responsibility of providing a clean, well-structured data feed shifts. It lies with the producer of that data.
The team that owns the source application or database.
Yes, they're the ones closest to the source, they know their data best, and they are best positioned to ensure it's canonical, clean, and lossless before it even enters the company-wide log.
That sounds like it simplifies the central data team's job.
Hugely. The data warehouse team, or equivalent, their job becomes much simpler. They just handle loading these already structured, high-quality feeds from the central log into their analytical systems. It decentralizes the data cleaning and structuring effort, pushing responsibility closer to the source, which improves organizational scalability. Teams own their data quality end-to-end.
And where should transformations happen? Before the log, in the log.
The ideal model, the book suggests, is for the data publisher to do initial cleanup and structuring before publishing to the company log. Create that canonical lossless form first, then any real-time value-added transformations, maybe joining streams, filtering, augmenting data, can happen as separate stream processing jobs that read from the canonical logs and produce new derived logs.
So transformed data becomes another stream.
Exactly. Other systems can then subscribe to these derived streams. Only aggregations or transformations that are very specific to the final destination system, like a particular data warehouse schema, should ideally happen during the loading process itself.
Right, and a major side benefit of this whole architecture is enabling these decoupled event-driven systems you mentioned.
Yes, it's a massive advantage.
Right.
Let's take LinkedIn's job view example again, which is illustrated really well in the book. When a job page is displayed to a user, the core logic for that web page itself is simple. Show the job details and record the event, user X view job Y at time Z with these attributes into the central log.
That's it.
That's basically it for the core page logic. All the other interested systems across LinkedIn.
Like
Hadoop for offline analysis, a security system may be looking for unusual scraping activity, the dashboard for the person who posted the job, recommendation systems figuring out related jobs, monitoring dashboards, tracking site health. They all just subscribe to that single job viewed event stream from the log and do their own processing independently.
So the job page code doesn't need to know about any of them.
Not at all. It doesn't need to change if a new data consumer like a new analytics feature is added tomorrow. This massively simplifies the logic of the core application and provides incredible flexibility. The system can scale and adapt much more easily.
Okay, but making this work for a site like LinkedIn, that central log has to handle insane scale, right? You mentioned billions of messages.
Hundreds of billions of messages each day, yeah. A huge number. To support this kind of scale, Kafka uses a few clever technical tricks.
Let's hear them.
First, partitioning the log. We take a single logical log topic, like page views, and chop it up into many independent partitions. Each partition itself is totally ordered, but there's no guaranteed global ordering between partitions.
Why do that?
This allows us to horizontally scale write throughput. We can distribute these partitions across many different servers in a cluster. More partitions, more servers, more throughput. Writers typically control which partition a message goes to, often using a key like a user ID. This ensures all messages for a single user land in the same partition, preserving order for that user, which is often what matters.
Okay, partitioning for scale. What else?
Second, we optimize throughput by aggressively batching reads and writes. Logs, much like traditional file systems on spinning disks or SSDs, are incredibly efficient for linear read and write patterns. Sequential I/O is fast. So Kafka groups many small message reads or writes together into larger, high-throughput operations, minimizing the overhead of network round trips and disk seeks.
Makes sense. Fewer, bigger operations are better.
Exactly. And finally, we employ something called zero-copy data transfer.
Zero copy.
Think of it like this. Normally, when data moves from your hard drive, say, to the network card to be sent out, it often has to make a few unnecessary stops in the computer's main memory and CPU along the way. Each copy takes time and resources. Zero copy is a technique that allows the operating system to move data directly from the disk cache to the network card, bypassing the CPU and user application memory entirely. It's like an express lane for data.
Much more efficient.
Dramatically boosts performance, especially for read-heavy workloads like serving data to many consumers. The cumulative effect of partitioning, batching, and zero copy is really impressive. The book quotes numbers like a single thread, being able to write hundreds of thousands of small messages per second, with replication and read even faster.
Wow.
This remarkable efficiency is what makes the log practical. Not just theoretically nice, but actually usable for universal data integration across an entire large organization.
Okay. So as you said, log in this context is really just another word for stream, which connects directly to stream processing.
Absolutely. Logs are central to modern stream processing.
So what exactly is stream processing? Let's define that a bit more.
Broadly speaking, you can think of it as infrastructure for continuous data processing. It's designed to process data as it arrives and produce low-latency results. But there are some common misconceptions. It's not limited to just SQL-like queries. It's not only for real-time, low-latency applications. You can process streams and batches too. And crucially, you definitely don't throw away the original data after processing it. The input log remains.
The book uses that great analogy of the U.S. Census, right?
Yeah, the 1790 census. It was a massive batch collection effort. People literally walked door to door over months to count everyone. That made perfect sense back then, given the technology.
Right. No internet.
Right. But today, with continued digital data feeds, births, deaths, migrations, website signups, you wonder why we still rely so heavily on periodic batch dumps for some things. Wouldn't it be more natural to just keep a continuous journal of these events, the stream, and produce population counts or demographic shifts as needed, maybe even in near real time?
So stream processing is adapting to continuous data.
Exactly. Many current data processes are still stuck in that batch dump mentality from centuries ago. With continuous data feeds, continuous processing becomes the natural, often far more efficient way to go. And it's sophisticated now. It can handle complex blocking operations like computing maximums or averages over specific time windows by having precise semantics for how those windows are defined on the stream.
So it's not just simple filters.
Not at all. Stream processing is really a generalization of batch processing, adapted for the prevalence of real-time data in our modern world.
Okay, but why specifically use a log for stream processing? Why not just have processing stages talk directly to each other?
That's a great question. There are several strong reasons why the light is so beneficial here. First, it makes each dataset multi-subscriber. Both the input streams and the output streams of a processing job are just topics in the log system, like Kafka. This means they're readily available to any other processor, or for debugging or for monitoring.
Ah, so you can easily tap into intermediate results.
Precisely. You can quickly tap into a stream, inspect its validity, maybe feed it into a separate testing environment, all without affecting the live production system. Very handy.
Okay, multi-subscriber. What else?
Second, and this is crucial for correctness, especially with things like database updates, the log reliably maintains order within a partition. If you're processing updates from a database to build, say, a search index, and two updates to the same product description arrive out of order, your search index could end up showing the wrong description. The log guarantees that processing order.
Prevents inconsistencies.
Yes. And the third, and arguably most important, use of the log in stream processing is to provide that critical buffering and isolation between systems.
The asynchronous point again.
Exactly. Imagine a processor that generates output faster than its downstream consumer can keep up. What happens? You basically have three options. One, block the upstream job. But that causes back pressure and can lead to cascading failures across your entire processing graph. Not good.
No.
Two, drop data. Sometimes acceptable, but usually not for critical information.
Definitely not ideal.
Three, buffer the data. The log acts as a very, very large, durable buffer. It completely decouples the producer rate from the consumer rate. The consumer can go down for maintenance, experience a temporary slowdown due to load, and simply pick up exactly where it left off in the log when it restarts. It consumes at its own pace without impacting the upstream data flow or losing data.
That seems essential for complex pipelines.
It's basically the only real option for building complex, reliable, multi-stage data flow graphs. This resilience is why popular open-source stream processing systems like Apache Samza and Apache Storm integrate so tightly with Kafka. They rely on it for this buffering and ordering.
Okay, that makes sense. Now, this brings us to one of the sort of perennial key challenges of stream processing, reprocessing data.
Ah, yes, reprocessing. The bane of many stream developers.
Because code changes constantly, right? New features, bug fixes, refining algorithms. If your code derives some output from an input stream, you'll inevitably need to recompute that output when the code changes. How do you handle that?
It's a fundamental problem. Nathan Marge's Lambda architecture became a very popular, though complex, approach to this.
Right, the Lambda architecture. How does that work again?
The core idea is you capture an immutable sequence of records, your input log. Then you feed this log into two parallel processing systems. A batch system, like Hadoop MapReduce, and a stream processing system, like Storm or Flink.
Two systems processing the same data.
Yes. The catch is you have to implement your transformation logic twice. Once for the batch layer, optimized for accuracy and completeness over large historical data sets, and once for the stream layer, optimized for low latency results on recent data.
And then you combine them.
Then you have to somehow stitch the results from both layers together at query time to get a complete picture.
Okay, pros and cons.
The pros are significant. It really emphasizes retaining the original immutable input data, which is good practice. And it squarely addresses the reprocessing problem. The batch layer handles that. The cons, however, are also significant. Maintaining identical business logic that needs to produce the exact same semantic result in two completely different, complex, distributed systems.
Sounds painful.
It is exactly as painful as it sounds. The operational complexity of running and managing two distinct distributed systems, keeping their code bases in sync, and merging their results correctly is, well, universally agreed upon as a major headache.
Even with frameworks trying to abstract it away.
Even abstraction frameworks don't fully solve that inherent operational burden. It's just fundamentally complex.
So is there a simpler alternative emerging?
Yes, thankfully. As an alternative to the operational overhead of Lambda, a simpler, more log-centric approach has gained a lot of traction, often leveraging systems like Kafka.
Okay, what's the model?
Instead of requiring two distinct systems, this model proposes, first, retain the full log of your input data in your log system, for example, and Kafka, configured with a sufficiently long retention period. Maybe 30 days, maybe longer, depending on your needs.
So keep the history accessible.
Exactly. Second, when you need to reprocess, maybe you deployed new code, fixed a bug, you simply start a second instance of your existing stream processing job. Start it from the very beginning of that retained data history in the log.
A second instance of the same job.
Yes. Importantly, you configure this new instance to direct its output to a new output table or data store. Not the live one.
Okay, processing in parallel to a new destination.
Right. Third, you let the second job run until it has fully caught up to the real-time stream. Once it's caught up, you simply switch your downstream applications to start reading from the new, correctly reprocessed output table.
Atomically switch over.
Ideally, yes.
Okay.
A clean switch. Finally, you stop the old version of the job and eventually delete the old, stale output table.
That sounds much simpler.
It really is. The advantages are pretty clear. Use a single processing framework which vastly simplifies development, testing, debugging, and especially operations. No more keeping two code bases in sync. You can even temporarily keep both versions of your process data available side by side. This allows for quick reverts if you find an issue with the new version, or even for things like A/B testing different processing logic against production data.
That seems like a really powerful and practical approach.
It's rapidly gaining traction precisely because it addresses the core reprocessing need without the immense operational complexity of the full Lambda architecture.
Okay, now another key aspect of stream processing is state. How do these processors maintain state? For things like counts or aggregations over time, or joining different streams together, they need to remember things, right?
Absolutely. Stateful stream processing is critical for anything non-trivial. And this is another excellent use case for the log concept itself. Remember our discussion earlier about the duality of tables and logs. A stream processor can maintain its working state, say, running counts or windowed aggregates, or the state needed for a join in a local fast table or index. Think something like an embedded database like RocksDB, or maybe even an in-memory hash map for simple cases.
Okay, local state, but what about crashes?
Exactly. To make that local state fault-tolerant, the stream processor, crucially, journals out a changelog for this local state back to the log system, like Kafka.
Ah, so the changes to its internal state become a log stream too.
Precisely. This changelog, itself being a durable, ordered log, allows the processor to instantly restore its exact local state if it crashes and restarts on another machine. It just replays its own state changelog up to the point of failure.
That's quite elegant.
It is. And it's powerful because the internal state of the processors is also maintained and externalized as a log, which means that state changelog can itself be subscribed to by other downstream processors if needed. You can build chains of derived, stateful data transformations.
Okay, but you can't just keep logs forever, right? They'd grow infinitely large. How does cleanup work? Log compaction.
Right, logs need management and cleanup. There are generally two main strategies, depending on the type of data in the log. For pure event data, things like page views, clicks, sensor readings, where each event is distinct and you might only care about recent history, Kafka typically supports retaining a sliding window of data.
Based on time or size.
Either. Often it's time-based, like keeping the last 7 days by default, or it can be configured based on a total size limit for the log partition. Older data beyond the window is simply deleted.
Okay, simple retention for event streams. What about keyed data?
For keyed data, like a database changelog where you have updates associated with a specific key, like an order ID or user ID, and you often only care about the latest value for each key.
Like the current status of the order or the user's current address?
Exactly. For that kind of data, Kafka uses a technique called log compaction.
Compaction. How does that work?
Think of log compaction like tidying up a messy financial ledger. For any given account, the key, you only truly need the latest balance entry to know its current state. You don't necessarily need every single tiny debit and credit from years ago if all you want is the current picture.
Okay.
Log compaction works similarly. It automatically garbage collects obsolete records from the tail of the log, meaning older entries keeping only the most recent update message for each unique key.
So it guarantees you have the latest value for every key.
Precisely. It ensures the log always contains at least the last known state for every key that has ever appeared. This allows you to still perfectly recreate the latest state snapshot of the source system by reading the compacted log from beginning to end.
But you lose the intermediate history for a key.
You do lose the ability to reconstruct all historical states for a given key, but you save immense amounts of storage space, while still preserving the essential latest state, which is often exactly what you need for replicating tables or caches.
Right, makes sense. So bringing all these ideas together, the log as the source of truth, stream processing, state management, compaction, the book paints a bigger picture, right, of the entire organization as a system.
Yeah, it really zooms out. It asks you to imagine your entire organization's systems and data flows not as this kind of disconnected patchwork of applications, but as components of a single, extraordinarily complicated distributed database.
The whole company as one database.
In a metaphorical sense.
Yeah.
In this grand vision, all your individual query systems, whether it's a Redis cache for speed, a SOLR, or Elasticsearch Index for search, or a Hive or Snowflake table for data warehousing, they become just particular indexes on your underlying organizational data streams.
Just different ways of looking at the same core data.
Exactly. And those sophisticated stream processing systems we talked about, like Storm, Flink, or Samza, they are simply very well developed, trigger and view materialization mechanisms.
Yeah,
They're continuously updating those indexes or deriving new materialized views based on the incoming data logs.
that's a fascinating perspective.
It is. And the author argues this perspective helps explain what people are truly doing with all these diverse data systems we see today. They're effectively just creating different types of specialized indexes and materialized views on top of a unified underlying data stream that's best modeled as a log.
Okay, this vision raises an important question about that explosion of types of data systems we discussed earlier. Why so many different systems if they're all sort of indexing the same underlying log data? The author suggests three possible futures for how this might play out, right?
Yes, three possibilities. The first is simply the status quo continues. Systems remain largely separate and specialized, which means external logs like Kafka remain absolutely vital for integrating them. Things stay complex.
Okay, possibility one, more of the same.
Possibility two is a kind of reconsolidation. Maybe a single monolithic Uber system emerges that tries to merge all these different functions, stream processing, batch, key values, search, graph, into one giant platform.
Does that seem likely?
The book argues it's pretty unlikely, just given the immense practical difficulties and complexity of building and evolving such a single, all-encompassing system successfully. Specialization often wins.
Okay, so what's the third, more appealing option?
The third possibility, and the one the author finds most compelling, is what he calls unbundling.
Unbundling.
Yeah. This is where data infrastructure is increasingly broken down into a flexible collection of highly specialized, often open-source services and APIs that work well together. Think of it as the Lego version of distributed data system engineering.
Legos for data systems. I like that.
Instead of building everything monolithically from scratch, you combine robust, proven building blocks. Maybe Apache Zookeeper for coordination, Apache Lucene libraries for powerful indexing capabilities, RocksDB for local state, and Kafka, of course, as the foundational backing log and messaging layer.
So you assemble systems from components.
Exactly. This approach, the argument goes, dramatically reduces the implementation time for complex, reliable distributed systems, potentially from years down to mere weeks or months, precisely because these reliable, flexible building blocks are finally emerging and maturing.
That's a powerful vision for the future. Now, when you look at building data systems this way, using the log as a central component, what's the single most transformative thing the log brings to the table for those individual services built around it? What complexity does it really take off their plate?
That's an excellent question, and the impact is transformative.
Mm.
An external reliable log allows individual systems, the search indexer, the cache, the analytics store, to relinquish much of their own internal complexity.
How so? What specifically can the log handle for them?
Think about it. A robust log system like Kafka can handle data consistency across replicas. It provides fault-tolerant replication itself. It guarantees commit semantics, meaning data written to the log is durably stored before acknowledgement. It offers external data feeds naturally, allowing other systems to subscribe. It provides the mechanism to restore failed replicas easily back to their correct state by replaying the log. It can even handle rebalancing data between nodes as your serving cluster grows or shrinks.
Wow, that's a lot.
It's a substantial portion of what any distributed data system needs to implement internally just to be reliable and scalable.
So what's left for the specific service to do?
The remaining complexity for a specific service, like your search system, is mostly about its unique client-facing query API and its specific internal indexing strategy or data layout, which is exactly the part that should vary from system to system based on its purpose. This allows developers to focus on the core value proposition of their service, rather than constantly reinventing the wheel for distributed systems primitives like consensus, replication, and recovery.
Okay, so the architecture looks like writes go to the log first.
Writes go to the log. The log captures all state changes durably and in order. Then, the actual serving nodes, the machines running your search index or your key value store, subscribe to this log. They asynchronously pull changes from the log and apply them to their own local specialized indexes or data structures as quickly as possible.
And reads go to the serving nodes.
Reads typically go directly to the serving nodes for low latency. Clients can even get immediate read-your-writes consistency by including a log position or timestamp they received from their write operation when they issue a subsequent read. The serving node can wait until it is processed up to that point in the log before responding.
What about the concern that this seems wasteful? You have the data in the log and copies in all the serving systems. Isn't that a lot of duplication?
That's a common initial reaction, but it's often much less of an issue in practice than it seems. Firstly, logs themselves are incredibly storage efficient. They typically rely on cheap, large hard drives and benefit from sequential I/O patterns and heavy compression. Secondly, the serving systems might need different hardware, maybe faster SSDs or more RAM for low latency queries, so separating storage concerns makes sense. And thirdly, the cost of storing the log is amortized over potentially multiple different serving systems or indexes that are all deriving their state from that same single log. One log can feed a search index, a real-time analytics system, an archive, etc. The cost is shared.
Okay, that makes sense. And LinkedIn actually uses this pattern extensively.
Yes, the book concludes with how LinkedIn has implemented exactly this pattern for many of its own real-time query systems. Whether the input is a log derived directly from database updates using change data capture, or a derived log produced by upstream stream processing jobs, these downstream query systems simply provide a particular partitioning, indexing strategy, and query capability on top of that underlying data stream from Kafka.
For things like search, the social graph.
Exactly. Their search indexes, their social graph store, their news feed delivery system, even some OLAP query systems are implemented this way. Kafka and underlying databases act as the durable system of record, and all changes flow reliably to the appropriate specialized query systems through that central log infrastructure. The serving nodes themselves are often relatively simple. Their main job is just to transcribe the feed provided by the log into their own optimized local data stores and serve queries off that. And critically, if the serving node fails, it can be quickly replaced and restored by simply having the new node replay the relevant portion of the upstream log.
So it simplifies building and scaling these complex query systems.
Enormously, it's proven to be a huge simplifying assumption for building and scaling their massive real-time infrastructure.
So to recap our deep dive then, logs, these seemingly simple append-only sequences, provide a truly principled and powerful way to model changing data as it flows through distributed systems and across entire organizations.
That's a great summary.
They act as the universal glue connecting disparate data systems. They enable the real-time processing of continuous changes. And they fundamentally simplify complex system architectures by handling core distributed concerns like consistency, replication, and fault tolerance.
What was once maybe an esoteric implementation detail buried deep inside database kernels is now a concept that's profoundly relevant to really any modern software engineer, data architect, or frankly, anyone looking to truly understand the fabric of our digital world.
Yeah, it feels like a fundamental abstraction we should all grasp. So, the final provocative thought for you, our listener, given that, as Jay Krebs aptly puts it, all of our systems are distributed systems now, how might thinking about your own organization's data flow, your own projects, through the lens of this humble yet incredibly powerful log abstraction, how might that change the way you approach your next big project, or even just a small data problem you're grappling with right now, something to mull over as you navigate your own data streams?